Well, thanks for the invitation to speak. It's a pleasure to be back in Bonn. All right. So this is a lecture on mean curvature flow in R3. So this, when I get to the new stuff, it's joint work with Richard Bamler. Let's see. So before I get into the meat of the lecture, just make two preliminary remarks. So one question is sort of how does this topic fit into the theme of the conference, Riemannian geometry and beyond? Well, of course, you can do mean curvature flow in a Riemannian three-manifold, but really the main point is that mean curvature flow is a process that gives rise to singularities, and the singularities play sort of a central role in the story, and that's how you're sort of forced to look at things that are more general than smooth surfaces, objects from geometric measure theory, and so on. So that's how this fits into the theme of the conference. Another point is that this topic or pieces of it get rather technical, and my plan is to avoid that as much as possible, and that's because this audience is rather heterogeneous. There are some people here who work in geometric flows or adjacent topics, but that's not my main audience. Okay, so I apologize to the experts. Those are not my main audience. Okay, so all right. So let me start with the definition. Okay, so suppose you have a smooth family of submanifolds of Rn. Okay, so we'll think of that as a manifold that's evolving in time. Okay. So this evolving manifold is a mean curvature flow if the velocity is equal to the mean curvature. Okay, so you can interpret the velocity of a moving submanifold as a normal vector field. Okay, and the condition is that like at every moment in time, that velocity vector field is equal to the mean curvature vector field of the submanifold. Okay. So you can think about this process in a number of different ways. So another would be, instead of looking at submanifolds, you look at parametrized submanifolds. Okay, so here you take instead you take some fixed abstract manifold n, right, and then you look at a family of smooth embeddings of that abstract manifold in Rn. Okay, and then the condition that it's a mean curvature flow is just that the time derivative of the mapping is equal to the Laplacian. Okay. So with the caveat, this Laplacian refers to the Laplacian of the pullback Riemannian metric. So at time t, you have an embedding ft, you pull back the Riemannian metric, and then you use the Laplacian associated with that. Okay, so that's an important point, because otherwise this would just look like the usual heat equation. Formally, it looks similar, has some similarities, but it's not the heat equation. Okay. So another vantage point, if you just think locally about mean curvature flow, let's say in the case of hypersurfaces, right? So locally an evolving hypersurface is a graph of an evolving function. So locally it's the graph of some, say, function ut defined as some open set, and then the graph of this time-dependent function is a mean curvature flow if and only if it satisfies this PDE. Okay, it looks like the time derivative of u is given by this expression. Main point being it's a linear combination of second derivatives where the coefficients depend on the first, and this gives you a parabolic equation. This right-hand side behaves satisfies an ellipticity condition. So analytically, this behaves like a heat equation. Okay, yet another point of view is that the mean curvature flow is the gradient flow for the area functional. Okay, so you think about the space of all surfaces, all submanifolds of Rn as some kind of infinite dimensional Riemannian manifold formally with the L2 metric. Okay, and then so then you can reinterpret the first variation formula from differential geometry. So as follows: so the first variation of area in the direction of a variation xi. So xi is some vector field defined along the submanifold, right? So this is, you take the inner product of h, then the mean curvature vector with the variation vector field and integrate, or, I mean, this is the same thing as taking the inner product of xi with minus h with respect to this L2 inner product. Okay, so formally, this says that the differential of the area is minus h. Okay, so if you flow in the direction of h, that's moving. That's the steepest descent for the area functional, formally speaking. Okay. All right, so a little history. Or context. So mean curvature flow can be thought of as a mathematical model for many physical situations. If you're in a physical context where you have a surface, maybe it's an interface or a membrane or something like that, and the energy is proportional to the surface area, and the mass or inertial effects are negligible, then the evolution will be given by mean curvature flow. All right. So this first showed up in the physics literature, in the metallurgy literature in the 1950s, but it shows up in different contexts. Another point is that you can think of mean curvature flow as being the first of sort of a very long list of other evolution equations where you start with mean curvature flow and then you add in other forces which are, say, small compared to the mean curvature or negligible compared to the mean curvature, and analytically or physically the theory would have something in common with the theory for mean curvature flow. In particular, if you want to study these more complicated equations, maybe you want to first study the mean curvature flow. Okay. Mean curvature flow also shows up. You can use it as a tool in various geometric and physical problems. You can use it to produce foliations or to try to produce minimal surfaces. And you can use it in general relativity, for example, constructing natural families of surfaces. So from the point of view of partial differential equations, the mean curvature flow is a natural analog of the heat equation when you're looking at an evolving submanifold. Okay, and it's a parabolic version of the minimal surface equation, something that's been studied for hundreds of years. And within the math community, this was really first taken, looked at seriously in the late 70s by Brocchi, but since then many different groups of mathematicians have been looking at aspects of mean curvature flow. There are people approaching it using the techniques of differential geometry, people using geometric measure theory, and then there are people from using more conventional or traditional techniques from PDE. But it's been quite challenging, and one has to borrow techniques from different areas to make progress. Okay. So for the remainder of the talk, I'm going to stick to the case, almost entirely to the case of surfaces in R3. Almost everything I say applies in three-dimensional Riemannian manifolds. If you replace R3 with a three-dimensional Riemannian manifold, subject to some reasonable, if it's non-compact, subject to some reasonable conditions at infinity, things will carry over. But mostly I'll be focused on dimension 3. Some things work in higher dimensions. Okay. So let's start by looking at some special solutions. So if you take a static plane, you just take a fixed MT is equal to a fixed plane, right? That's a solution. Or more generally, if you take a minimal surface, right? A static minimal surface is minimal if the mean curvature equals 0. Okay, so that's an example of a solution to the mean curvature flow. And philosophically, that shows that mean curvature flow incorporates the theory of minimal surfaces, right? As a PDE. So it's sort of strictly more complicated. Maybe the first interesting case is the case of a shrinking two-sphere, right? So let's take MT to be a two-sphere centered at the origin, radius RT, where RT is square root of 1 minus 4t, right? So the idea is the sphere has mean curvature pointing inward, so it's going to shrink. As it shrinks, the curvature gets bigger, so it shrinks faster and faster, and shrinks to a point in finite time where the radius is given by this. And another example to think about is the shrinking cylinder. So we take the product, say, of a circle in the plane, circle of radius RT, and I cross that with R, so we get this shrinking round cylinder where the radius is given by this formula. Okay, so notice that in both cases the solution has curvature that blows up in finite time. Okay, and the solution is only defined for a finite time interval. Okay, so those are some first solutions to consider. Now, what about some general properties? So you have short time, existence, and uniqueness. So this is well posed for short time. If you have, say, a compact smooth surface N, right? So then you get existence of a unique solution for short time. Okay, and that can be prolonged uniquely to some maximal time interval. So this gives you some unique mean curvature flow defined on a time interval from 0 up to capital T. So where the initial condition is you're given compact smooth surface N. All right. So here this refers to the maximal interval of existence, and in fact, this capital T is finite. So it only exists for a finite time, and moreover, the second fundamental form, which I'll denote by A, okay, that blows up as you approach this blow up time capital T. Okay. So, of course, saying that it exists for finite time and the curvature blows up doesn't tell you an awful lot about what's going on, but something bad happens. Okay. Now, a fundamental property of mean curvature flows is avoidance. Okay. So if you have let's say you have two mean curvature flows, M and M prime. Okay. So these guys are, let's say, they're compact smooth surfaces evolving, and they're both defined on the time interval from T1 to T2. Right, so they avoid each other, meaning if they're initially disjoint, so M intersect M prime is empty at time T1, then the same thing is true at later times. Okay, and this is an easy consequence of the maximum principle. So if this were not true, if they're initially disjoint, right, they would have a moment where they first intersect. If you look at an intersection point, modulo translation and rotation, you can assume they intersect at the origin with horizontal tangent planes, and locally that would tell you that locally in time you see the surfaces are graphs of two functions, and one function is strictly bigger than or equal to the other. Okay, so if you write that down, the fact that this is a parabolic PDE, that would contradict the maximum principle. Okay, so this fact is a consequence of the maximum principle. So a variation on this is what I would call self-avoidance, which says that a mean curvature flow, it can't. I mean, if you have two different mean curvature flows, they can't bump into each other. A variation on that is that a single mean curvature flow can't bump into itself either. Okay, and so one way to formulate this would be as follows. So suppose you have a mean curvature flow. Let's say it has uniformly bounded curvature as you approach T0. Okay, so it's defined from a half open, half closed interval from 0 up to T0. If the curvature remains bounded as you approach T0, then in fact this guy will limit to an embedded surface as you approach T0. So you can't have a situation where you have smooth surface which then touches itself. Okay, and this is also proved using the same kind of maximum principle argument. And in fact, this is embedded in this assertion here. Okay. Anyway, all right. So now let me give you a glimpse of the scheme of the lecture. So I'm going to continue by looking at a little bit of phenomenology, looking at some special solutions or special classes of solutions, and that's going to move us toward trying to understand what happens at this blow-up time, and particularly want to understand the formation of singularities. Okay, so that will be kind of the next segment, discussing singularity models and singularity analysis, and then from that I want to transition to flowing through singularities or flowing beyond singularities. Okay. Okay. So I want to give a disclaimer here. At time constraints, I'm going to be somewhat informal at times, and I'll certainly have to omit many important aspects. Okay. Okay. So let's look at the simplest case of instead of looking at surfaces in R3. Okay, let's go down a dimension and look at curves in the plane, right? So now, curvature flow is just curve shortening flow, or we're looking at a curve whose velocity vector field is equal to the curvature vector. Okay, and so you have this theorem of Hamilton and Grayson that goes as follows. Okay, so let's say you have a curve shortening flow where the initial condition is connected, right? So you have just a single smooth embedded curve sitting in the plane. Okay, so then so as I mentioned before, this blows up in finite time, but here in the R2 case, the behavior as you approach the blow-up time is very simple and transparent. Okay, so as you approach the blow-up time, the diameter of the curve goes to 0, and in fact the curve itself is Hausdorff converging to a point. Okay, so it's kind of converging to a point. Not only that, if you translate and rescale to normalize, say, the diameter, okay, then as modulo that translation and rescaling, the curve is converging to a round circle in the smooth topology as you approach the blow-up time. Okay, so it disappears, but under a microscope, it's converging to a round circle. Okay, so that says that even for an arbitrary initial curve, asymptotically, you see the same behavior we saw before in the simplest situation where you have a shrinking round circle. Okay. All right, so let's go back up to dimension 3. So Huysken showed that you have similar behavior for convex surfaces. Okay, so if you take mean curvature flow with convex initial condition, say compact convex surface, then you see the same thing. Okay, blows up in finite time, shrinks down to a point, and becomes asymptotically round. Now, if you drop the convexity assumption, things start to get more complicated. All right, so maybe the simplest case to look at is a torus of revolution. Okay, so take a torus of revolution where you revolve a circle around the z-axis. Well, let's take a circle whose radius is small compared to the axis you're revolving around. Okay, so this radius of the circle here is small compared to this. So what you get is a torus of revolution, which is kind of thin. All right, and under those conditions, the mean curvature will point inward, and this torus of revolution will shrink, and the symmetry is preserved. So what happens at blow up is that it will collapse to a circle. Okay, so you see again blow up of the surface everywhere, but instead of collapsing to a point, it's collapsing to a circle. Okay, and then there's the phenomenon of a neck pinch singularity. So here, let me just start with this diagram. So you take a surface which has, say, two roughly spherical regions joined by a neck. Okay, this could be a surface of revolution. Then the mean curvature flow looks like this. So what you see in this neck region, what you see is something that's starting to look a bit like a round cylinder. Okay, remember the round cylinder kind of shrinks. As it shrinks, the curvature gets bigger, and it shrinks even faster, right? So you have this instability where this neck region kind of gets ahead of the rest of the surface, and actually what happens at blow up is away from a single point, the surface has a smooth limit. Okay, and at this point, so you say take the Hausdorff limit, you get some non-smooth object. Okay, it's a smooth surface if you remove that point. Okay, now you can try to understand what's happening at that singular point in the case of the neck pinch by doing a blow up analysis. Okay, so what does that mean? So you want to kind of zoom in, to compensate for the shrinkage that's occurring under the evolution, right? So this refers to rescaling or parabolic rescaling, which is the symmetry of the equation. So let me just formalize this. So suppose you have a mean curvature flow. So then for any scale factor r, if you scale the surfaces by r inverse and scale time by r squared, you get another mean curvature flow. Okay? So so another way to think about this is in terms of the space-time picture. Okay? So let's look at the space-time track, which is just for every t, you take the surface at time t, you cross it with the singleton t, so we're kind of inserting it at height t in space-time. Okay, take union over t, that's the space-time track, and then the assertion is that for every r, if you look at the image of the space-time track under this parabolic rescaling, which maps x comma t to rx, r squared t, then you get the space-time track of another mean curvature flow. Okay? So that's just, these are just two different ways of saying the same thing, but this is a useful point of view. Okay? So let's apply this kind of rescaling for a neck pinch. Okay? So if you take, let's say the neck pinch we had in that cartoon a moment ago occurred at the point x0 and r3 at time t0. Okay? So the blow-up time is t0. So then let's translate things in space and time. Let's move x0 to the origin and shift t0 to time 0. Okay? And then we'll do this parabolic rescaling. Okay? So we can look for each positive scale factor r, we can look at this rescaled version of the flow. And so, right, again, the surface has a neck pinch singularity, and we're trying to zoom in to see what happens, not just at a single surface, but at the whole evolution. Okay? And the claim is that when we do that, as r goes to 0, in the limit we actually see round cylindrical flow. Okay? So it's really becoming converges to a round cylinder as a flow. Okay, so in the picture, here's what you see at time -1 after rescaling. Okay, so if you look at this family as r goes to 0, this is what you see. Okay, just a picture expressing what I just said in words. Okay, so you could ask what happens more generally. Okay. So, what are there other types of singular behavior than a cylinder that can occur, or the case of a shrinking round sphere that can occur? All right, and the natural enlargement would be to look at solutions to mean curvature flow that just shrink self-similarly in time. So the mean curvature evolution is unchanged modulo scaling. Okay, so this is the notion of a soliton, or shrinking soliton. Okay, so shrinking soliton is just a mean curvature flow of the following form. The surface at time t is just equal to a fixed surface n times the square root of negative t. Okay, that's if you're normalizing things. So it's the evolution is defined for negative time. Okay, more generally you can so this guy would become singular at the origin at time 0, and you can do the same thing with different space-time centers. Okay. Another way to think about this is the following. So if you look at the surface here at time -1, right, which is just n, so saying that this family of surfaces is a mean curvature flow is the same thing as saying that this surface n at time -1 satisfies this elliptic PDE. Okay, that the mean curvature of this surface n is equal to minus h over 2, x over 2 rather, perp. So what x is the position vector. X is the position vector, and at a point on the surface, you divide that by 2 and take the normal part. You project it to the normal space, and the requirement, or if there's a minus sign, the requirement is the mean curvature equals that vector field along the surface, and that's an equivalent to saying that this thing is a mean curvature flow. It's also equivalent to saying that the surface n is a minimal surface, not with respect to the Euclidean metric, but with respect to an appropriate conformal deformation of the Euclidean metric. Okay, so examples. Well, we already saw shrinking round spheres and cylinders. The next most interesting example was discovered by Ongeneth. It's called an Ongeneth torus. So that's a torus of revolution. It doesn't look like the thin torus of revolution we talked about before, which collapses to a circle. It's sort of fat, but not too fat. Okay, and somehow manages to just as it collapses, it shrinks down to a point. Self-similarly, but it turns out there are lots of shrinkers, although it took a long time to construct them rigorously. So there are examples. Kapelowski and Muller and Nguyen around roughly 2015 constructed examples of arbitrarily large genus. So these were conjectured based on numerical evidence long before. But so these look roughly as follows. So think of a plane passing through the origin and a sphere centered at the origin. So those intersect along a circle and meet orthogonally. Okay, and now think about desingularizing that object by inserting kind of along the curve of intersection some kind of rescaled bent version of a second Shirk surface. Okay, so if you know what the second Shirk surface is, it's a surface, minimal surface in R3, which has a Z symmetry. It's invariant under discrete symmetries in the vertical direction, because if you blow it down, you see two planes intersecting orthogonally. Okay, so you think of taking that and you're kind of wrapping it around the locus of singular points. Okay, and for large genus, that they show that can be perturbed to be an exact solution to this elliptic PDE. Okay, so potentially any shrinker, it can play the role of the shrinking round cylinder. In fact, it was recently shown under some mild conditions, I won't state, that this is true. If you have a shrinking soliton, then you can find a compact surface, which actually, when it blows up, you will see that given prescribed shrinker at blow up. Okay. But the main remark here is that it seems that the problem of classifying these guys is intractable. For the same reason, nobody knows how to classify, say, bounded finite genus minimal surfaces in R3. These are conventional minimal surfaces, and so there doesn't seem to be any even a program or hope of classifying these objects either. Okay. Okay, so now, the shrinking solitons serve as potential models for singularities. But what happens in general? I mean, if we have a general, if we have a blow up and we look locally what happens there, what can we say? All right. So this leads to the idea of singularity analysis. And if you're familiar with the theory of minimal surfaces or minimal integral currents or stationary currents, then you're aware that theory is based on a monotonicity formula, which allows you to say at a point in your singular minimal surface, you can rescale the minimal surface, pass to a subsequential limit, which will be a cone, a minimal cone. Okay, and this is kind of the cornerstone of the theory. It allows you to develop dimension reduction and build a whole theory. So there's a similar idea going on here, which is initiated by Huysken. So this goes as follows. So let's take some point in space-time, x0, t0, and then look at the following kernel. So it looks like a heat kernel. So at x comma t, it looks like this. So this is think of this as like a backward heat kernel starting with a source at x0, t0, with the caveat that it's not the three-dimensional heat kernel. It's actually the formula is borrowed from a two-dimensional heat kernel, and that's because we're going to integrate it over surfaces. Okay. Okay. So now take a mean curvature flow, MT, and Huysken defines the Gaussian area of that flow at some time t, little t less than t0, as follows. So you look at the surface at time t, and you look at this kernel at time t, and you integrate that over the surface with respect to area measure. Okay, so we're just taking the weighted surface area at time t, where this kernel right depends upon t, and so that's we'll call theta with the space-time center at x0, t0 at time t, and the key result is this monotonicity claim, right? That the Gaussian area is not increasing. Okay, so if t1 is less than t2, okay, then the Gaussian area at the earlier time is less than or equal to the Gaussian area at the later time. And moreover, if equality holds, then you're on a shrinking soliton. Okay, so here, and this is proven by a formula. The time derivative of this Gaussian area is given by this expression here, non-positive expression. The integrand vanishes if and only if you're on a soliton. Okay. So the first consequence of this is that if you give yourself some point in space-time, x0, t0, right? So then, since this is a non-increasing function, it has non-increasing function. It has a limit. Okay. As you approach t0, which is the density. Okay. Now. Okay, so let's think about how you'd apply this monotonicity formula. And again, you can think about the parallel with minimal surfaces if you're familiar with it. So let's say we have a smooth mean curvature flow blowing up at time capital T, and first consider a base point where the base time t0 is strictly less than t. So we're looking at this before blow up occurs, all right? And let's say that we choose a point x0 on the surface at time t0. So we see a smooth surface, okay? And we're going to base our kernel at that point in space-time, right? So this kernel is going to be concentrating down like a Gaussian at this smooth point on the surface. So it's not hard to convince yourself, if you kind of rescale that surface, what you're seeing is like you're integrating a Gaussian over the plane in the limit when you get 1, okay? So so this will tell you that actually the density is 1 in this case. But now if you take now let's go back to a more interesting case where t0 you look at the base point where t0 is equal to the blow up time, and now let's say a singularity is forming at this base point x0 t0. Well, then the density may be larger than 1, okay? And so a key remark here is that it turns out the Gaussian area is actually scale invariant. Okay, so if you take a mean curvature flow and you perform this parabolic rescaling, the Gaussian area is unchanged. And so if you combine that with the fact that the Gaussian area has a limit as t approaches t0, that will tell you that if you apply parabolic rescaling to a given flow, asymptotically, so you have a family of mean curvature flows which have asymptotically constant Gaussian area. Okay, they're converging to the Gaussian density of the original flow. Okay, and so in particular, when you do this rescaling process, again, we already did this before in the case of a shrinking round of a neck pinch, but now we're doing it in general. So what we'll see is if you have a subsequential limit of this family, as r tends to 0, then that subsequential limit will have constant Gaussian area, okay? And therefore, by Huysken's monotonicity result, it will be a shrinking soliton, okay? And such things are called tangent flows. So the caveat is nobody said that you can extract a subsequential limit, okay? So this is a fundamental result of Elmanen. So he showed in '95 that in fact, this rescaled family does converge subsequently to a smooth shrinking soliton, okay? But it's not may not be what you think. What he proves is it converges weakly, okay? In the following sense. So you look for every r, you have a mean curvature flow here. So that's an evolving surface. Replace each surface with its area measure, okay? So then the mean curvature flow becomes an evolving measure, okay? And the assertion is that this family of evolving measures converges subsequently in some weak topology to the evolving surface measure for a shrinking soliton, okay? With the caveat that you may not see the surface measure of the shrinking soliton, but possibly some integer multiple. It might be 2 times the area measure or 3 times the area measure, okay? And so Elmanen made this remark. He said the reader should beware that the convergence to the blow-up might not be smooth. Okay, there might, in principle, be small necks and other topological kinks that pinch off and disappear. Okay, so just emphasizing that this is really weak convergence. But he also made the conjecture that the multiplicity that you see in the limit, right, is equal to 1. So you don't see 2 times or 3 times the area measure of the shrinking soliton, you see 1 times that, okay? So that's the multiplicity one conjecture of Elmanen. And he noted that if this conjecture were true, then actually this kind of nasty behavior doesn't happen, okay? A posteriori, if the multiplicity is equal to 1, then in fact the convergence is smooth convergence, okay? A posteriori, okay? All right, so now I want to shift gears and look at flow through singularities. Okay, so so here, let's start with the same example we had before. Okay, so then we have this neck pinch forming, right, becomes singular, but then we want to prolong the flow beyond that. Okay, so so that's the cartoon for the project. And the motivation, there's several motivations for this. So first of all, from a PDE viewpoint, right, you expect a theory of weak solutions to the PDE. So thus far we've been talking about classical or smooth solutions to the PDE, but just like with you know, the minimal surface equation or harmonic map equation or harmonic map heat flow or Navier-Stokes or whatever, you know, you expect for one reason or another, maybe for physical reasons or other reasons, you expect to have a theory of weak solutions or generalized solutions. Okay, so this is just one instance of sort of a long established agenda in the analysis of PDEs. Another is from the point of view of physics. If you think of mean curvature flow as a mathematical model for physical systems, then the physical systems you're interested in exhibit this kind of behavior. I mean, you just saw from the animation something that, you know, that kind of looks like what a soap film does when a neck pinch occurs. And then also, if you're interested in using mean curvature flow for applications in mathematics or mathematical physics, almost all the applications require you to have a process which passes through, which continues beyond the formation of singularities, right? Unless you make very strong assumptions on the initial conditions, you need to develop this theory, okay? Okay, so so this has been a project underway for decades. I mean, as I said, since the late 70s. And over time, people developed a series of conjectures. Okay, so this is just a partial list. And these are, some of them were folklore, others showed up in the literature in different forms. But here's a version of the conjecture. So the first is that there should be a flow that has a reasonable set of singularities. Okay, so you want to have a flow that has a space-time singular set contained in a finite collection of curves, right? So think about the example of this thin torus of revolution, which collapses to a circle. There, the singular set is just a circle. Okay, so you're not going to get the singular set to be smaller than a curve or a collection of curves. People contemplated different scenarios, and no one was ever able to come up with anything that was much worse than this. Okay, so that's the origin of the first conjecture. The second is basically the conjecture that I already mentioned of Ilmanen, but Ilmanen's conjecture was what happens at the blow-up time. So it was a conjecture about smooth mean curvature flows and what happens at the first blow-up time, but this would be extended to the entire process. Now the generic singularities conjecture, again, there are different versions of this out there. The idea is that if you take an arbitrary initial surface, it might happen to have some very delicate hidden structure which allows very special delicate singularities to form, like these high genus examples. But maybe if you allow yourself to perturb the initial condition a little bit, the perturbed surface when it evolves, will not give rise to complicated singularities, and this is the spirit of Huysken's conjecture. For generic initial conditions, you only see spheres and cylinders as tangent flows. And then there's a conjecture of White, which is that if you start with an initial condition which is diffeomorphic to the two-sphere, then you have a unique flow, and again, the singularities are simple. They're modeled on spheres and cylinders. Okay. Yeah, just a remark. So these are not conventional mathematical conjectures because, right? So I haven't defined the flow here, right? So you have to figure out what that means, and then you may also have to struggle to interpret these statements. Okay, but that's part of the reality. Okay. So the short version of the rest of the talk is these conjectures are all true. So we proved a little bit more than a year ago. Okay, and so what we built on a series of significant advances that were occurring over the last 5 to 10 years. Okay, and of course it goes further back in time. So I want to talk about that trajectory. Okay, so that's what I'll be doing for the rest of the talk. So let me just mention there have been various approaches to flow through singularities. The first one historically was due to Brocchi, called Brocchi flow, and then level set flow and flow with surgery. I'm not going to say anything about flow with surgery due to time limitations, but it is a useful approach. Okay, so Brocchi flow. So if you're going to talk about a generalized solution to the equation, then you're no longer talking about smooth surfaces, right? So you need to decide what you're going to replace smooth surfaces with, okay? And then you need to figure out how to impose the equation on them. But for Brocchi flows, you're evolving varifolds, or integral varifolds. So this is a definition due to Almgren. So if you have a radon measure mu, it's an integral varifold. If mu is the sum of mu i's here, where mu i is a surface measure on a C1 surface restricted to a compact subset, okay? So the simplest case to consider would be just the area measure on a C1 surface, or if you take two copies of the same surface, and you add those up, you get twice the area measure, or more generally, you just take a bunch of surface fragments. You think of it as like a superposition of surface fragments, okay? Now, for these guys, there's a version of the first variation formula that came up earlier, right? So there's a version of the first variation formula I'm not going to write down, but it generalizes this first variation formula from before. And in particular, it gives you a linear functional on C1 compactly supported vector fields, okay? And this gives you a vector value distribution, which you can think of as the distributional mean curvature of this integral varifold. And so now here's the definition of a Brocchi flow. So you have a family μt of radon measures, where μt is an integral varifold for almost every time. Also, for almost every time, this distributional mean curvature should be somewhat well behaved. It's supposed to be absolutely continuous with respect to μt for almost every time. And then this evolving family of measures should satisfy the mean curvature flow equation weakly. Okay, so I'm not going to say exactly what this is, but if you take the smooth mean curvature flow, okay, so if the MT is the smooth mean curvature flow and these are the surface measures, then you can check that if for a test function phi, the following equation holds if you integrate the surface at time t over, well, I'm missing a domain of integration here. I'm integrating this over mt on both sides. So the time derivative satisfies this equation for any C1 test function in space-time. So the actual condition is a perturbation of this. It's kind of an integrated version of this, and you replace the equality with an inequality. Okay? Now, yeah, well, it works in any dimension or in Riemannian manifolds. Yeah. Okay, so some properties. So first of all, you get existence for any smooth surface of a Brocchi flow. The calculation for Huysgen's monotonicity formula holds, so you get the monotonicity formula. You have an epsilon regularity result. It tells you if you have a Brocchi flow and the density at some point in space-time is close enough to 1, then the flow is smooth, backward in time locally. There's a compactness result. So this is all good news. The bad news is that if you take, say, a shrinking round sphere and then you just throw it away at some time, okay, that's a Brocchi flow. So that's just a feature of the definition. It's sort of underdetermined. So that's an unpleasant feature of Brocchi flows. Another one is that the Brocchi flows that were constructed by Brocchi, okay, they may not have this particular pathology in its construction, but the thing is that they don't have the density bound that's needed in order to apply his regularity result almost everywhere. Okay, so there's sort of a mismatch between his construction of solutions and his regularity theory, and this is really due to you can think of this as a version of the multiplicity problem that goes right back to the beginning of the subject. Okay, okay. So now let me talk about level set flow. So this was introduced around 1990. So here, instead of having evolving measures, you have evolving closed sets. Okay, so you take a family KT t in some time interval, where these guys are closed sets. And the first requirement is the space-time track, right, defined as before. That should be a closed subset of space-time. And the second condition is just we're imposing the avoidance property by as an axiom. Okay, so you require that if you now have a smooth mean curvature flow that's defined on some time interval from t1 to t2, which is a subinterval of I, right? So if this smooth mean curvature flow is initially disjoint from your evolution at time t1, it should remain disjoint. Okay, so that's the same avoidance property we had before, but we're just requiring this as an axiom on this this evolving family of closed sets. Okay. And then the level set flow within a given initial condition C, let's say a compact subset of R3, is the maximal weak set flow starting from C. Okay, and it's not too hard to prove that there exists a unique maximal weak set flow. Okay, so properties. Well, the first is that you get existence and uniqueness of solutions almost by definition. Not only that, you get it for any compact set. So that sounds pretty good. Also, if you look at the level set flow starting from a compact surface, well, then it agrees with the classical flow for as long as the latter is defined. Okay, so that's kind of a reality check. So that's also good. Level set flows avoid each other. That's also good. But the bad news is that level set flows can fatten. So you can start with, say, a compact smooth surface. The level set flow at some point will develop a singularity, then after that the set has non-empty interior. Okay, so this is really unsatisfactory from the point of view if you're thinking of this as a notion of evolving surface. So it's by containment. Okay, so they're partial. If you take these weak set flows starting from C, they're partially ordered by inclusion. You basically take union and take closure and verify that's also a weak set flow. So that's the level set flow. Just by that, what I just said, you take union and take closure. Yeah. Okay, I'm going to skip this. So there was a hybrid notion with some nice features I just want to mention. So Illman and Hershkovitz-White did the following. So you give yourself now M0. It's a compact smooth surface. And then let D plus be the compact domain bounded by this compact smooth surface that you get from Jordan separation. Okay. Then you can look at the level set flow of this D plus. Okay. And then you take the space-time boundary of that, which I'll call K plus. So, all right. So you take the surface. You look at the inside. Instead of involving the surface, you involve the inside by the level set flow, and then you take the space-time boundary. That you call the outermost flow. And you can do the same thing by using the inside, using the outside instead of the inside, and that's the innermost flow. And it turns out that these guys are these are still weak set flows, and there's also a Brocchi flow which lives on top of them. Okay, so this is sort of a partial reconciliation of the two approaches. Okay, I'm running a little short on time. Speed up a little bit. So around the year 2000, there was a breakthrough by Brian White, who showed that if you have a mean convex surface in R3, then the list of conjectures I had before holds. Okay, so mean convex surface is mean convex if the mean curvature points inward everywhere. Okay, so it has positive mean curvature. Okay, so for example, if you have a convex surface, that's mean convex, but with a little bit of care, you can construct one of these dumbbell surfaces, which has which is mean convex. Okay, and so his theory would apply to such a dumbbell surface. Okay, so in particular, yeah, maybe I'll. Yeah, okay. So you have a level set flow starting from a mean convex surface. So it's non-fattening, so that pathology does not occur. You also have a canonical associated Brocchi flow. He showed that the space-time singular set has Hausdorff dimension at most 1, and the singularities are modeled on round spheres and cylinders. Okay. Okay, I think I'll just skip over that stuff. Short on time. Okay, so now I want to come to the new results. So the first is really a new definition or a new setup for for flow through singularities, which we call almost regular mean curvature flow. All right. So so that is defined as follows. So for some time interval I, you're looking at a weak set flow M. So this is a subset of space-time, right? Which is closed and has the avoidance property as before, right? Which satisfies two additional conditions. So the first is easy to state. It says that you see a compact smooth surface for almost every time. Okay. And to state the second one, I need to introduce the notion of the regularity scale, or the parabolic regularity scale. Okay. So for that, so I need the parabolic r-ball. So the parabolic r-ball centered at a point in space-time. So that's p x0 t0 r. Okay. That's just the usual r-ball centered at x0 times a two-sided time interval. Okay. So it's centered at t0 and as duration r squared in both directions. Okay. So that's this space-time version of a ball adapted to the parabolic scaling of the equation. And now the parabolic regularity scale at a point is roughly, it's sort of the supremal scale at which you see controlled complexity for your flow. Okay? So in the following sense, okay? So for a given point x0, t0, this local scale, so it's a supremal r with the following property. So we look at our parabolic ball in space-time, right? Parabolic r ball, and then we look at time mt for various t. Okay? So the first requirement is that everything which intersects that parabolic ball should be regular, should be smooth. Okay? And the second is that it has sort of controlled geometry at that scale r. So you can pose this in different ways, but we require that the normal injectivity radius is at least comparable to r. I have a factor of 10 to the minus 2, but that's kind of a negotiable constant. Okay, so that just says if you look at the normal exponential map restricted to the vectors of length less than this this number, then it gives a diffeomorphism. Okay, so if this point is two remarks. So if this point is singular, well then the local scale is 0, right? Second, if the local scale is positive, which means in particular that the solution, the mt t0, if it passes through this point x0, it's smooth. Okay, so then you can look at the second fundamental form there. Okay. The second fundamental form gives you an upper bound on the normal injectivity radius. If the second fundamental form is big, then the injectivity radius is small. Okay? So if you reverse that, it tells you that you get an upper bound on the second fundamental form by a constant times this the inverse of the scale. Okay? So this R-loc inverse plays the role of sort of an enhanced curvature. Okay? And so the second condition is just that this quantity, this curvature-like quantity, is in space-time L2. Okay, so for every t, you integrate this over this time t slice with respect to area, then integrate over time. That should be finite. Okay. Okay, so this, so it's not hard to see. This is a short argument to show that this gives rise to a Brocchi flow, which is even multiplicity 1. And so we prove several the main results about these guys. So first of all, there's a compactness result. If you have a sequence of these guys whose initial conditions converge smoothly, then these almost regular flows will converge subsequently to an almost regular flow. You get a version of the Multiplicity One Conjecture. So if you have an almost regular flow, then any tangent flow is a multiplicity 1 shrinking soliton. And then we combine these theorems with some of these earlier results that I was referring to. Okay, so this is a result about generic singularities. These two are about the mean curvature singularity conjecture. So I'm running short on time, so I'm just going to leave it at that. So by combining our work with this earlier work and doing a bit of work, you get the following. So if you take any outer or innermost flow, particularly any non-fattening level set flow, that's an almost regular flow. And then you have these estimates for this, the space-time singular set, and moreover the tangent flows, except for possibly finite in many points, you see tangent flows which are round spheres or cylinders. Okay. Let's skip this next result. And then we have the generic singularity result. So if you start with an arbitrary compact smooth surface M, so then you can approximate that and see a smooth topology with a sequence of surfaces Mj, such that if you look at the level set flow starting from Mj, then it's non-fattening, so it has the regularity that I just mentioned. Okay. And all tangent flows are round spheres or cylinders. Okay, so generically you only see these simple tangent flows. And then in the two-sphere case, right, so you have a level set flow whose initial condition is diffeomorphic to S2, then it's non-fattening, so you have the regularity I mentioned before, and all tangent flows are round spheres or cylinders. Okay. Sorry, I'm running short on time. Okay, so let me try to indicate how we approach the first version of the Multiplicity One Conjecture, which was Ilmanin's version for what happens at blow-up time for a smooth mean curvature flow. So let's shift time so that the flow blows up at time 0, okay, defined, say, for some negative time. So two scenarios to think about are as follows. So maybe, right, maybe the surface looks locally at some small scale r like a catenoid. Okay, so catenoid is this, right? It's a surface, minimal surface of revolution, right? If you scale that down, then it will converge to a multiplicity 2 plane. Okay, so if it looks at a very small scale like a almost like a catenoid, then at a larger scale you could see this multiplicity developing. And a variation on that would be the following: you might have at time t, you might see two spheres that look like they're shrinking self-similarly. Okay, they have nearly the same radius, but then they're joined by a very, very small catenoidal neck. Okay, so you actually have a connected surface, and you could have potentially similar behavior. Okay, so these are scenarios to think about, and the heuristics are: so if the surface looks locally like two sheets, right, then they won't tend to move toward one another. Okay, that's kind of like a maximum principle fact. However, the catenoidal neck which joins the two sheets, could exert an attractive force between them and tend to pull them together. Okay, so that's what we're concerned about. Okay, and for these special examples, and if the neck, say the catenoidal neck has some tiny scale r, and it looks epsilon close to a catenoid after you rescale, right? So after rescaling, that would allow it to move at speed epsilon. Okay, so that means that the original neck could, just by the way parabolic rescaling works, it could move at speed epsilon over r inverse. Okay, so you could have this tiny neck that's just moving around at very high speed, which sort of goes back to the scenario that Ilmanin was describing. Okay, so let me just give sort of a very quick sketch of how we would rule out these scenarios. So we would define what we call a separation function. So S at a point x is going to be kind of the distance to the other sheet. Okay, so think about the case of the two spheres joined by a small catenoidal neck. Away from the catenoidal neck, if you have a point on the surface, there's sort of another sheet nearby. Okay, so take the distance to that other sheet. So that's well defined away from the catenoidal neck. Okay, and it turns out that log of this is actually a super solution to the heat equation. Okay, and then we look at the same that Huysken's kernel from the monotonicity formula, this ambient Gaussian. This turns out to be a subsolution to the conjugate heat equation. Right, so we use this and we look at a quantity like this. So you take log of the separation function, which satisfies the nice equation I had before, and then you take log of this local scale function and we blend the two together. So away from the catenoidal neck, we use log of the separation function, and near the catenoidal neck we use log of the scale. Okay, and we blend them together using this eta, which is a cutoff function, and we integrate that against this kernel, okay, the Huisken kernel. And so just doing a straightforward calculation, you can rule out the scenarios. Using this quantity, you can rule out the scenarios that I was talking about. Okay. Now, in general, nobody said that the solution looks like that. Nobody said the solution looks like two sheets with a catenoidal neck. You might have multiple sheets, or you might have a minimal surface more complicated than a catenoid, right? But you might have, but in some places in space-time, it doesn't look like either of those two cases. All right, and so so the idea is sort of quantitatively we can control the part that doesn't look either sheet-like or minimal surface-like, and then in the rest of it we can have some version of this calculation that I indicated there. Okay. So I'll stop there.